Today, I'm going to continue investigating this approach to generating random variates. As I mentioned, that there are three generic approaches and a multitude of special cases, which we won't get into. And in looking at things, I'm going to spend a little bit more time on this. Of the three general methods, which are all in the reading, I'm just going to cover this inverse transform method that we'll talk about today, and something called the composition method, which I've asked you to read a little bit about. And we'll talk about that basically today and tomorrow. There's a third general method called the acceptance rejection method. That's also in the reading, but we won't be covering it, and I won't be making you responsible for it. However, the thing about this random variate generation is that it's a little more important than you might think. The thing is that at some point in the future, you may be in a situation where you need to be generating random variates having particular distributions. And if you're doing it in Java, then you can use the facilities in Simkit, which are available, if that's an option. If you're doing it on some other platform, in some other language, then it's possible that they may not have the particular distributions that you want. For example, in Java, if you recall, the random class had things like next Gaussian and next exponential, I think. Those were the two, and uniform. So you could do those three. But if you wanted to do something else, then you would need to use one of these methods that we're talking about. So it's important to understand where these are coming from. It's important to understand the idea of these pseudo-random numbers that are underlying this whole thing, and how these methods transform those uniform random numbers into random numbers having a particular distribution. And again, the word pseudo is always implied throughout all of that. Okay, with that, let us see what's on tap for today. Okay, I'm going to do a couple of more inverse transform examples. Last time we did the uniform, the general uniform between A and B, just two of them. We did the right triangle, which was based at 0 and looked like, if you remember, it looked like this. So here was 0, there was some value B, and then the PDF looked like this. And as part of this, it's important to understand the difference between a PDF, which is what this is, and the CDF, the cumulative distribution function, which is technically the integral of the PDF. And well, if we were to be doing a deeper dive into all of this, then we would get into some calculus. At some point, that might come up with some things I might be having you do. But again, calculus is something you've all at least had a refresher on and have learned at some point in the past. So that's kind of there. All right. So if you remember last time we did again, the one where it looked like this. And now we're going to do one that sort of flips it. So this is a left triangle because it's leaning toward the left now. And again, we're going to use one parameter b. So it's going to be based here at 0. That's just for simplicity. And so its support is going to go from minus b to 0. In other words, these, if you were to generate from these random variables, again, having this PDF, they would all be negative. And that's something to just kind of keep in mind for later. So the PDF for this, again, our parameter b, we're going to assume is bigger than 0 in this particular case. So that we could have made b a negative number, but that's not how we're doing it. Okay, so in that case, the PDF has this form, minus 2x over b squared. And that's because b is for negative b less than x less than 0. In other words, all the random variables are going to be negative. That shouldn't come as a complete shock that there are negative random variables. All the random variables we've been dealing with so far in our simulations have generated positive values. That's true for exponentials, the uniforms that we happen to have chosen. The gamma distribution has always generates a positive one. But if you remember from your statistics class, there was something called the normal distribution or the Gaussian distribution, and that had both positive and negative values. So it shouldn't be a big shock that there could be random variables that generate negative values, because the normal happens to be one of them. Okay, so this is our PDF. And remember, notice that the PDF functions are always positive or non-negative. So when we see a minus sign, we need to sort of check on that to make sure that this quantity is always going to be, is this in fact what this line is going to look like? And the thing to remember is that x now is going to be negative values. And since x has negative values, negative of a negative is positive. And so it should not come as a huge shock that this is the equation of this line. And it turns out the CDF turns out to be this value, 1 minus x squared over b squared. And again, just sort of a rough check on that. If we plug in b to our CDF, then it would be 1 minus b squared over b squared, which is 1 minus 1 or 0. Okay, and that should match what the picture is telling us, because remember, the CDF is the probability that the random variable is less than or equal to that value. So the probability that this random variable, click on the pen and it doesn't, I want a different color is what I want. So the probability that we get values down here is going to be 0, because this will only generate values between minus b and 0. And likewise, if we plug in 0, we see that 1 minus 0 is 1. And so, in other words, the probability that this random variable will have values bigger than 0 is that is less than or equal to some value up here is going to be 1. That because all of the area is to the left of all the points up here. So let's go back to red. All right, so our CDF actually is going to look like, well, let's see, how do I have, no, I don't graph it, but it's going to, if we kind of look at what this is going to be, what it's going to be like. It's going to have a curve. Now, there are two ways to get the CDF from the PDF, but the thing is that the CDF is what we need for the inverse transform, because that's the function that we need to invert in order to find the expression that we're going to be plugging our uniform random number into. But for simple functions like this, we don't have to go all the way to calculus. We can just go to basic geometry. In other words, the area under the curve for some x that's between minus b and 0. Okay, so what we can do is we actually want this area. That's what we want. However, what we can do instead is first calculate this area here and then take 1 minus it. So the area here would be the length of the base, which is x. So the area of a triangle is 1/2 the base times the height. And so the height is minus 2x over b squared. Where did that come from? Just plugging x into the formula. And so the area of this shaded triangle is simply x squared over b squared. You know, all we needed was the area of the triangle, but that's not the area we want for the CDF. We want this area here in the white, and that would be 1 minus that. Why? Because the total area under the triangle is 1. The area of the shaded region is x squared over b squared, so the area of the white part here is 1 minus that, or 1 minus x squared over b squared. So for simple ones, that's what we can do. Now for the problems I'm going to be asking you to do, I'm going to be asking you to do something comparable to this, and the math is actually going to be a little bit more involved, but you won't have to do any of this because your starting point is going to be the CDF. So you're going to have to do a little bit of work to invert the CDF, but you won't have to do the calculus to turn the PDF into the CDF. And we'll see what all of that is about. That will be posted tomorrow. Okay, so now that we have our CDF for in our important region here, we need to invert it. And the way we invert it is always the same. We take some u, and then that u, by the way, is going to be in the interval 0 to 1. Why? Because the range of the CDF, the cumulative distribution function, is always between 0 and 1, because the CDF is a probability, and probabilities are always between 0 and 1. In other words, remember, its definition is the probability that our random variable is less than or equal to the value at little x. So, and probabilities are always between 0 and 1. And so this u that we choose here, or just as our variable, is always going to be between 0 and 1. And what that means is that, so even though the full definition of the CDF has to have these 3 values, if we want to, because the CDF is always defined on the entire real line. It's always defined for the entire thing. In other words, this 0 and this 1 are part of the definition, and these ranges are part of the definition. But the only piece we need to worry about is the one here, which is where the values are always generated. Okay, so we can always take u strictly between 0 and 1. And so in that region, our function has this form. And now it's just a simple matter of algebra. So so here, what do? We kind of move this to the one side, we move u to the other. So X squared over B squared is 1 minus U. X squared is this. And now again, when we take the square root, you always have to do the plus or minus because it could be either one. And if you remember yesterday for the situation where we were like this, we chose the positive root because the support of the random variable, as it's called, or the place where the random, the possible values that could be generated, in this case, were always positive. But in this case, the support is negative. See, because we're actually in this situation. So all the values are going to be negative. So we have to choose the negative root. That's important. If you choose the positive root, then it's not going to be correct. So the inverse transform method, therefore, is we generate a U uniform 0, 1. Again, when we implement it, we just do a call on our random number generator. And then we return this expression, this inverse function with U evaluated in it. In other words, minus B, and it's root 1 minus U. That's the that is the functional form of that. Okay, moving on. Now let's look at exponential. So exponential is something that we've been dealing with. And see, do I have functions? Okay, well, but what the exponential PDF looks like this. And again, it's important to know that it's not just this form over the whole line. It's that form only for positive values. So in other words, if we were to graph this, why are you not? I want a different color here. Okay, so the way, if we want to look at this, for values less than 0, the PDF, again, this is the PDF I'm graphing, is 0. And then it actually looks like this. It's called exponential because that's the exponential function. And the height of this is 1 over lambda. And that's because in this particular parameterization, the mean turns out to be lambda. And that's how sometimes you'll see that flipped. Sometimes you'll see it lambda e to the minus x times lambda, and for that the mean is 1 over lambda. So, but here we want to parameterize our exponentials by the mean because that's the way we've been doing it. So this is our PDF, and it looks like this. And again, the important thing when we're just looking at the mathematical expressions is to understand that this 0 is a key part of it. That is, this expression does not hold for the whole real line. It only holds for values x bigger than 0. Okay, and then this is going from the PDF to the CDF is an elementary, this is where we need calculus. So now you're not, I'm not going to make you responsible for something like that, but it would look something like this. This is how you would do it. You would actually, the PDF for the CDF is always defined to be this. And we need to have like a different, this is, strictly speaking, this is always true. But, and this is, remember I said the 0 is important. So we can't just plug this expression in. What we have to do is we have to break it up into its 2 pieces. Okay, and now we can, when we unravel this is the expression that we get. And again, I'm not gonna make you do the calculus here, but you know, if you're, I would encourage you to at least kind of you know, work through that. And remember, you know, kind of dredge out your old calculus notes, because just because, you know, calculus is just one of those things that you never know when you're actually going to use it. So, okay, so let's apply our inverse transform method. The point is that this 0 we don't have to worry about. We only have to worry about the places where things are positive, but we still need to be somewhat mindful of the fact that something like that's going on. Okay, so we want to find the inverse of the CDF. And you know, the thing about this is that if you do some research or enter Googling, which passes for research these days, you will find descriptions of various random variables, and they will typically give you the PDF and the CDF, and then the mean and the variance and things like that. So you don't necessarily have to grind through the calculus of figuring out the CDF from the PDF. But for some reason, they will typically not give you the inverse CDF. So that's something that has to be worked out. All right, so again, to find the inverse of a function, you always start with this. You pick a variable, you set it equal to the function, and then you try to solve for the argument of the function, and that gives you the inverse. Okay, so for our u values, and again, so to say, this is how it would look graphically. So we would pick a u, go over until we hit the function, drop down, and then that gives us our inverse. So that's what we're doing algebraically here. We're setting u equal to the function and then trying to unravel it. So again, here we bring the e to the other side, bring u to the other side. And then now here's the thing. When we take the log of both sides, because log is also a monotonic function, then we can always do that. So don't forget the minus. So the minus is down here. So minus x over lambda is the natural log of 1 minus u. And so now we can solve for x. So here's our solution. And so our inverse function, the inverse of the CDF function, is minus the lambda times the log of 1 minus u. Now, the minus should cause a little bit of concern. Why? Because the values have to be positive. And because the values have to be positive, we see a negative, and we need to make sure that this expression is always going to be positive. So now let's look at this log of 1 minus u. Well, u is always going to be between 0 and 1. Oops, this is u. And therefore, 1 minus u is going to be between 0 and 1. And the log of a number that's between 0 and 1 is always negative. And so a negative of a negative is going to give us a positive. Okay, so again, it's always worthwhile to sort of check for something that's just sort of nonsensical. In other words, if for some reason this expression could ever be negative, then that would mean we would be generating negative values, and that can't be right in this case, because exponentials are always positive. So now our method is to generate our uniform and return minus lambda times the natural log of 1 minus u.
Arnie, can you say, so when you're passing in u, what is U is the set of numbers. I'm trying to remember.
No, U is a uniform 0, 1 random variable. So when I say generate U, I mean generate, get a uniform random number that is a uniform 0, 1 random variable. And then plug that value into this function, and that will generate a random variable that has an exponential distribution and whose mean is lambda.
So Simkit is creating the actual number U, the actual number that is assigned to you when you do uniform 0, 1.
Well, I'm glad that you asked that, because what we're going to do now is we're going to do that. We're going to implement that in Simkit.
That's what I'm saying, because that number you're retrieving is from a series of numbers that, like, whatever you had, like 2 to the 25,000 or whatever it was. I don't have it in front of me.
Yeah. Now hold on to that thought, because we're about to do that. Okay. So what I'm going to do now is remember this right triangle that we had. That we did this yesterday. So we're just going to sort of take that. And remember that our inverse function was this b times the square root of u. Now, Simkit has been designed so that you can, it's easy, or well, it's straightforward to implement your own random variates that can be used interchangeably with the ones that are built into Simkit. And there are actually two choices. There's a random variate interface. You notice that since day one, we've always defined our random variable, say like inter-arrival time generator or service time generator, all those, they've been defined as random variates as a type. And the reason for that is that in Simkit, there's this random variate interface. So what that allows your models to do is to be agnostic about what distribution that is. In other words, if I have an arrival process and I want an exponential, then I give it an exponential random variate. But if I want like a uniform, as we've done in another assignment, I can give it a uniform, but I don't have to change the arrival process to reflect that. And if I wanted to give it a gamma, or even something like a Poisson, or just any other random variable that would produce positive values, including these triangles that we're about to do, then I can put those in. So there are two choices in Simkit, depending on how lazy one is. One is to implement the random variate interface. And the other is there's also an abstract base class called random variate base, which is it actually just implements the random number piece. So what I'm going to do is I'm actually going to choose the first choice here, just to show you all of the details of that. And this, I believe, will answer the question that was just raised. And then now all we need to do is we just need to tell the random variate factory where to look, and then it will be able to find our stuff. And I'll show you how that, what that's about. Okay, so let's fire this up here. I think I'm sharing my whole screen. So can you see my NetBeans?
Yes.
Okay, good. All right. So what we're going to do is I'm going to implement this right triangle. Now, this isn't totally necessary, but when naming it, the convention is that if you say if you sort of have the name of the distribution followed by variate, then it's just an indication of this is going to be a random variate. Okay, so we're going to implement the random variate interface. Okay, and then we need to fix our imports, and we see that Simkit random variate is there. And if we want to see the Java doc, we see that the random variate is an interface, and it has these 4 methods. It has a method called generate, which we sometimes have been using. It has get and set parameters, and those are going to be the parameters of our distribution. I'll show you how that gets used. And then the other is a random number. So that is what is required by our random variate interface. And so let's implement all of those. Okay, so the first thing is this random number. That random number instance is going to be creating our uniform guys. Just by convention, I like to call it RNG. It doesn't really matter what it is. Never read, don't worry about that. Okay. So to set it, again, since this is part of the interface, we need to actually kind of do that by hand. Okay, so we'll never actually call this. These methods, the set and get, the set random number is actually called by the random variate factory. We'll kind of see that. Okay, so the second step is to add our parameters, and there are kind of 2 ways of two mechanisms for this. So here, remember, it was a double. Let's call it the left. I'm going to call it left. This is what we were calling B. Okay, and then since it's kind of like a parameter, we want to have setters and getters. Okay, we've done all that before. And remember that we were insisting that B had to be positive. So if B is less than or equal to 0, we're going to throw an exception. Oops. And I just noticed that I called this left, but that was not, this really should be called right. So now I don't know if you remember this. One of the nice things about this refactor thing is that if I want to change the number, I can refactor it, and that will also, notice that also changed my all this stuff. Okay, that's just to, if not B, should be right. And we'll just make sure that we note that. Exception if B is less than or equal to 0. All right. So now here's the thing, that the random variate factory actually uses this set parameters thing, and then the getter needs to return an object, an array of objects. Okay, so the getter for that is fairly straightforward. The setter for that, the set parameters, Now, remember that, notice that this is a var args because we don't know how many there are going to be. So, so here's what we need to do. First, we need to check that there's going to be at least one of these. We can be strict and say there has to be exactly one. So let's do that. So if the length of the parameters is not equal to 0, then we're going to throw an illegal argument exception and say, you know, you have to have exactly one parameter, and this is how many you gave me. Okay. Now, what else can go wrong? Okay, since this is an object, it may not be numeric. Let me see a question. Kind of a written example. Yeah, okay. Okay, so now I've given you one parameter, but because it's an object, you know, why is this an object? Because you don't know what kind of parameter it is. There are all kinds of different parameters. In fact, there are some random variables whose parameters are like just arrays of numbers. So it doesn't have to be numeric, but in this case, it needs to be numeric. Okay, so so how do we check that? So if we make it to this next line, we know that there's at least one. And so, and here's how we can, the way to check it is to say, is it an instance of number? In other words, remember, number is the one object wrapper for all of the numerical types. And so that what that means is that I can give you an integer, I can give you a double, I can give you a float, I can even give you a short. But if it's instance of number, then we can actually set it. So we can set our right by casting it to a number and then just getting the double value from that. Okay, but if it's not a number, we need to throw a new illegal argument exception again. And here's what you gave me. Okay. And then just as one final thing, as one penultimate thing, it's always useful to override the toString method and return what we have. Otherwise, we're going to have that gobbledygook. And let's just return our value. Okay, so now this is all the setup that we need to do for our parameters. And actually what we can do at this point before we get to the main one is just sort of verify that we can actually find it. So let's see how we can actually tell the random. What we need to do is first of all confirm that everything is copacetic. And we also need to confirm that the random variate factory can actually find it. So here's how we do that. We tell the random variate factory to look in the package that our random variate is. And it's called add search package. And we tell it, in this case, it's mv3302.random. So that tells random variate factory, when you're looking for a random variables, look here. Okay, so now we can use the get instance method for right triangle and give it a value. Let's make it 2.5. Okay, so how can we verify that we found that? By printing it. So what I'm looking for is, I'm looking for, oops, this should be a print line. Okay, so see there? That's what my toString was giving me. And notice that I'm, right. Now something is off here. Because this should have been misspelled. It might have grabbed the one from Simkit. See which one it grabbed. It might have right trial. It was grabbing the right one. But what? All right, we got that. Huh? Okay, so right, so now what we want to do is we want to generate. All right, and so now this is going to give us a whole bunch of errors. Why is it giving us? This should give me errors. There we go. That was, I know what was happening. What was happening was, it was, must have exactly one parameter. Okay, so if params, oh, it's not equal to 1. Duh. All right, let's. Okay, we have to make sure that it's compiled. There we go. Okay, so now we got to here, but okay, what was going on? We have an unsupported operation exception. Okay, so that was that was what I was expecting. What was going on, just so you know, what was going on before was that it was actually picking up the previously compiled one. So with this, because the random variate factory is kind of looking in the compiled places, we need to make sure that it has been compiled. One way to do that, by the way, is to set our property to, let's see, where is it? Where is it? Compile and save is disabled. So, okay, so we need to explicitly recompile it each time. Okay, so now we are ready to generate. And how do we generate? We want to use this formula right here, b times the square root of u. And this should finally answer, hopefully, the question. So the random numbers have a method called draw to distinguish it from generate. And okay, so what was it? It was the logarithm of u. And it can't find that symbol, but oops, actually the method is actually log. And there's, why is that? So they called the natural log, instead of ln, they called it log. Okay, so now, okay, so you know what? Why wasn't it doing that? See this little thing right here? See this little, I don't know what that symbol is. That shows that it has not been compiled. So we need to compile that. Okay, so it generated a negative value. Why did it generate a negative value? Because I did not give it a I was doing the exponential. This should have been the square root. So that shows you that this was not pre-planned at all. Okay, so let's compile that, make sure we compile that. And then when we run it again, we are going to get a positive value. Now, I have a question. Do you all know the R package? Are you familiar with that?
No.
No. When you had your statistics class, what did you use?
Calculator, pencil, and paper. For the first one, probability. Yeah, for our first class that I think it was supposed to be more probability, we didn't use any programs like that I can recall.
So when you did statistical analysis, did you use a program for that?
Right now we're using Jump.
Jump. Okay. Okay, now I know R better than Jump. So here's the thing. Here's the question. What I'm going to do, what I want to do is I want to generate a bunch of these and show a frequency histogram. So I'm going to do that in R, but you should be able to do that in Jump as well. Okay. So my example will be, and you could do it in Excel too. That will require a little bit more. So here's what I want to do. I want to sort of verify that this will actually generate values that will result in a triangle PDF. And the way to do that, or a way to do that, is to generate a whole pile of them, save them to a file, and then create a histogram of that and see what the shape of that looks like. Okay, so the first thing is I want to create a file. So I'm going to hardwire just some of this stuff. And then what I'm going to do is I'm going to say, oh, let's create a file writer for the text thing. And then if he wants to surround this with a try catch, that's fine. actually what I need to do on, I don't need this anymore. Actually, as it turns out, what we want to do is we want to define this outside here. This again and that. Okay. Why? Because we want to, and then it's also just writer. Okay, so what I'm going to do, or let's decide on how many we need. Let's just start with 100, but we're going to have to do a boatload more of those. But this is just to make sure. And then we're just going to append not to hex string, to string, our generated value. And then for the buffered writer, we're going to give it a new line. Okay, so what this is going to do is it is going to, and then let's just close everything. Actually, strictly speaking, this should be in a finally, but that's all right. So here's what we got. So it gave me 100 values. That's fine. So now let's give it a boatload more. Let's give it, let's give it 1,000,000 values. Okay, so it seems to be too large. No problem there. Okay, so now I have a whole bunch of values that have been generated by this. And what I'm going to do is, okay, I'm going to fire up R. Again, this is, you can do this in jump. And so what, here's how we do it. There's a, let's, I have to read and then, projects MV what is it called? And E3 class code is what it's called. And then what is the name of the file? It was right triangle.txt. Could not read. Let's see. Fat fingering this here. All right, so let's, oops. Oh, let's make it read. Okay, yes. Yeah, jump is going to be a little bit nicer than this for you. So, all right. So now what I can do is sort of plot it like this. And I think, okay, so actually, I want to, oops. Oops. Okay, so the thing to note is that this is actually giving a, I mean, it looks kind of linear like that. A couple things to check. Notice that it's only generating values between 0 and 2.5. In this particular one, since I said set frequency to be false, the height is going to be 2 over b, which is 2 over 2.5, which is going to be what? 2 over 2.5, which is 0.8, which is pretty much what we have here. Okay, so and now you can basically do this in R as well, but what this is shown, again, when you look at the shape of this, then you see that it's not, it looks fairly linear. So even though this square root function is nonlinear, it actually produces a PDF which is linear. So now, there was a question about how, when we were looking at this, let's see what we're looking at. Well, or something like this. There was a question about what is U? So has that been answered? Do you understand what U is now? This is U. And every time that this gets called, then you get a new value of U. And so a new value gets put into the square root function. And so a new value gets generated here. Okay, I've gone a little bit over, but that's actually all I have for today. So I'm going to give you the rest of the hour off. And in the chat, there was a request to go over a written homework example. I would be happy to go over a more complex example tomorrow. And and then we'll just kind of take a look at tomorrow. We're also going to look at this composition method as well, and then see another example of implementing it in Simkit. So so that is it for today, and I will see you tomorrow.
Arnie, just follow-up question on you.
Yeah.
So when you're saying, so uniform generator is just it's just uniformly generating a number in between 0 and 2.5, and that's what becomes U.
Not quite. U it generates between 0 and 1. So U is uniform 0 to 1.
Okay, so Simkit is generating a number randomly, pseudo-randomly between 0 and 1, which is then plugged into the formula.
Correct. Yeah, so it's this formula that gives us the triangle. This would only give us the uniform. So actually, let me do this just to kind of show you. What would happen if we just returned U instead? Okay, so let's compile this. Okay, I'm going to run this again. And then let's see, just want to make sure I'm sharing the right things here. Oops, let's see another. Okay, so now what I did is I'm just returning U now. So let's see what U generates. Okay, so if I don't apply this, what's going to happen? Well, okay, now I just created a whole bunch of these. Let's read it in. And then look at our histogram for that. So now you see what we're getting? In fact, look at this. Between 0 and 1, the height is roughly 1 as well. So what this is demonstrating, and now this is obviously not a right triangle. This is what this random number thing is giving us. It is giving us a random variable that is uniformly distributed on 0 to 1. So there are several pieces to this. One is it always gives us a value between 0 and 1. Second, the uniform part means that the height of our PDF is going to be 1. And that's kind of, notice it's not exactly that, but that's because we were just generating a bunch of them. But it's pretty close. If we were to do a statistical test on this, this would show that these are indeed look like uniform 0, 1 random variables. So U by itself is just uniform. But when we take that U and we apply a function to it, oops, we don't have a main method there. Let's run the main method. When we apply the function to it, and now read it back in and do our histogram, then we get this. And if we were to do another distribution, a similar distribution, but one that had a different shape, if we were doing it correctly, we would get a shape that looks like that. And this is just kind of a way to verify that what we've done is more or less correct. So for example, again, remember I had this mistake first because I had the exponential kind of in mind. So if that's the case, compile it. What would happen if I kind of forgotten about that? Well, let's see what data that produced. Okay, so it produced basically a negative exponential. So notice that it's all kind of on the negative side here, and this actually kind of this actually has kind of a rough exponential shape. So if I use the exponential instead of the square root, or the log instead of the square root, then I get something which is not the correct thing. But just to make sure that everything is correct here before I commit it, then, and this is what I'm looking for. So if I were to get something like what I just did, then that would show me, that would be an indication that I had not correctly written my generate function. Okay,